All right. As for today, so going to look at applications of second order differential equations. And without a doubt, the most interesting application is our all lovely springs. So mechanical vibrations, and we're going to look at a spring. So some notation to define. So we have a spring of length L, little l, all right, when it is in equilibrium position, in its natural position. And then we hang a mass on it, M, all right, when you attach the mass to the spring, all right, it stretches to a length of L, capital L, what we are calling. This is where we define actually that equilibrium position where we define our starting point at U equals 0. So that is our initial distance of 0. And let's always make positive direction down, all right? Although it should still work in both directions. Once again, we're going to use Newton's second law of motion. And again, position is U equals 0 in the equilibrium position. Now, though, all right, we are going to have a second order differential equation. So before we looked at this with velocity, now we're actually turning this into a second order differential equation. And that's why, right, we just love this formula so much, because you can do first order and second order differential equations. Let's identify our forces. So we have gravity, all right, mass times gravity, all right, whether that's 32 or 9.8, depends on the situation. And then our spring force, all right, is negative. We're using Hooke's law, right? F equals kx for a spring. And our distance, right? So it's the distance offset of the natural length from our position. And we have that constant k. That's the one we're always going to need to be solving for. Since we identified u as 0, then I can actually reduce that constant to negative k times L. All right, we're going to talk about that a little bit more in a minute. Then we have, all right, so those are the two that are always on it. Then damping, our damping forces that we're going to investigate. We're going to start with undamped forces, but damping, right, something that acts against the motion. That one's always negative. And then some external force or some resonance, some forcing function, whatever we want to investigate there. So when we put all those together, here's what our equation becomes. All right, second derivative of position, gravity, all right, the spring, the damping, and the forcing function. We can then rewrite that, all right, to get our second order differential equation on the left side, and then a bunch of constants at a function on the right side. In order to find, all right, the Hooke's law coefficient, we can set gravity equal to that, since they are going to be opposing forces always. And that means that'll help us solve for the function. That also means that those, since they're always going to negate each other, oh look, our function actually even further reduces, all right, to 2 derivatives of position, and then 3 variables that have to be input or solved for in our equation. Also, the other thing, we're always going to have to identify our initial conditions, all right? So some initial displacement, if any exists from the equilibrium position, and any initial velocity. So all of these are going to be about identifying our information. We are going to start with the simple case of free undamped vibrations. So if I get rid of the forcing function and I don't have a damping on there, oh look, my equation 2 of the f of t becomes 0 and gamma becomes 0, which means our equation actually reduces, all right, to this guy. And then this, I could solve this characteristic equation. It just becomes the complex solutions. And I'm going to call this omega, all right? So this actually exists in the forcing function, all right, omega 0. it also can be, it can be identified by solving the characteristic, and that's typically how I'm gonna do it. But we're gonna see later that this omega can be equal to omega 0 when there's resonance. And so we can solve it by identifying it's a ratio of Hooke's loss function divided by the mass. This also brings up one other thing. So when I solve this, right, when I solve this characteristic equation, this would be our solution, all right? And the big thing here is that I have a summation of sines and cosines. When you have a summation of sines and cosines, it's always going to be better using I can use some difference and some polar coordinate equivalencies. And I can actually turn this into this. Okay? Notice that I have a lot of the same pieces, all right? Still have omega 0, I still have t. Okay, but now I find these r and deltas, which I can solve for based on C1s and C2s. The issue is that why would I change something that has sines and cosines into just cosine?
To get the real answer, like the non-imaginary part of it.
No, this is the real.
Okay.
Right? No imaginary here. Why would I prefer this? All right. And it looks like, right, I have three. Actually, I have three constants in that one, so that's actually just
one curve.
It's one curve. A sum of sinusoidal functions versus a single sinusoidal function. When you add two together, do you know what that looks like?
It's janky, right? It's not like
it's still this, but I can't identify. Notice amplitude, phase shift, right?
Period.
Phase shift, amplitude, period. Yeah, like I was like, I have all those pieces there. So it's always better whenever we can to reduce it down to that. Now that requires a little bit of algebra trig, right? But why would I leave it like this when I can turn it into this? And that's the real beauty of these functions. Now, we're not always going to be able to do this, so when we can, we want to. That's what I want to emphasize. And then notes about masses. Again, we're in the metric system. All right, we have kilograms. If we're in the standard system, right, we're going to have slugs. Yeah. All right, so everything starts with let's identify information. Oh, one other note right here. Tangent only works if this is what over what? Tangent is what over what?
Sine over cosine.
Sine over cosine. So super important, right? That's why I always try and write cosine first. Okay. Otherwise, this won't work out. But if you write sine first, as long as you flip that, it'll be fine. Just one little note that I want to make sure I identified. Okay. So let's identify our information. A 16-pound object stretches a spring 8/9 of a foot by itself. There are no damping or external forces, so that is excellent news. You can get rid of those immediately. The spring is initially displaced 6 inches upward from its equilibrium position, given an initial velocity of 1 foot, 1 foot per second downward. Find the displacement and time t. Remember, downward. And again, I really like this. It should work both ways, although we were talking that one problem didn't quite work out. Okay, so some information. Weight equals 16 pounds. Our capital L, right? The displacement of the object. So capital L is displacement from equilibrium position. Or natural position. So 8/9 of a foot. Now, here's the other thing. I can set up my initial conditions. So initially, that means what's our time? Initial velocity, initial displacement.
Our time is 0?
Time is 0. Okay, so initial displacement is 6 inches upward. So 6 inches.
-6 sets our positions down, or positives down.
Absolutely correct. So I'm going to do -6. 6 inches, 8/9 of a foot, 1 foot per second.
So we got,
Divided by 12.
yeah,
So little easy stuff like that is gonna kill us, right? So just make sure. All right, -6/12, so -0.5 feet. All right, same thing, and then 1 foot per second. And so when we identify info, it's good to have all that clearly identified. Okay. That looks like pretty much everything we need to identify. Now we can actually start to put it into our equation. So W equals mg. Once again, I'm going to use 32 feet per second. I know it's not the exact value, but it makes my numbers nice.
yeah, it does.
So gives me 0.5 slugs. Then, all right, the other thing is always to find K. We're always going to use our mg equals KL equation. So I need these pieces, all right? I could also use W here. But this is always basically the first step because this is always going to be part of our equation. We have, this all starts with a spring. All this is based on spring. So I need to identify my K.
It's just G over L.
And this does have units, all right, which we could identify, but since they're going to be a means to an end, I'm not worried about it. All right, so our equation becomes 1/2 u double prime plus 18u equals 0. We're starting with our general form here. All right, second derivative, mu double prime plus ku equals 0. So the only things I actually needed were k and m, and I can set up my equation. And then let's put this. And then I have a differential equation, all right, that we can solve. So setting it up is going to be everything. And then the rest, I was like, this is what we just did on the chapter 3 test over and over again. Characteristic equation. Solve that guy down, plus or minus 6i. Now, here's the big thing. Also note, I always recommend solving a characteristic. You should be, I mean, it's just solving a quadratic. Be pretty good at that and then identifying. But omega 0 equals square root of k all over m. 18 divided by 0.5, which, oh look, gets me 6. That value, that is omega 0. Okay.
Cool.
So I could identify that value by either solving the characteristic or by just plugging it into this equation, either way. And in the undamped case, this is without a doubt. Even in the damped case, when we have external forces, only solve the characteristic. But there are little other shortcuts when we have specific cases. Once these are the homogeneous cases specifically. So we get our equation, all right, from our characteristic or by using omega 0 and plugging it in. Then we need to take derivatives because before we go into reducing it down, I need to solve for C1 and C2. Okay, so our function would be ut equals -1/2 cosine of 6t plus 1/6 sine of 6t. But now we get, when I have it in this simple form, this is the case where I can solve for r and delta, all right, my phase shift, my period, all the pieces, all right, and I can actually write this in a better form. So once I have C1 and C2, then I can use these, which are, if you recall, your polar conversion formulas. All right, and I can turn this into a single sinusoidal, aka specifically cosine function. And again, I'm going to use fractions and exact numbers when I can, but this is one of those cases where no. A lot of these numbers get very, very rough, very, very quickly, as you'll see in the fun of the whole thing. Okay, here's also the fun thing if we recall from our trig. Okay, there are two possibilities. Or tangent. Either in quadrant 2 or quadrant 4. All right, when tangent is negative. So let's take a moment and let's recall a few things. First of all right, over here, quadrant 1, yes. I mean, what are the SIGN signs of sine and cosine?
Both positive. Only y is positive. Both negative.
Exactly. Okay. Tangent is then a ratio of sines and cosines, right? So where is tangent negative?
2 and 4.
2 and 4. All right, exactly as we just stated. But here's the funny thing, right? What's the period of sine and cosine?
Like
just their general functions. What's their period?
0 to 1.
Period.
2 pi.
2 pi. What's the period of tangent?
Pi over 2.
Pi.
Pi.
Because it's negative pi over 2 to positive pi over 2. It's actually kind of funky, which means that tangent repeats every pi. So it actually is off by pi half the time in just the standard unit circle. That's what makes tangent weird. Which means that this isn't just our number, and the calculator specifically, because I just put this in my calculator, right? And this is radians. So make sure your calculator's in rads. All right, that's the big thing. So in your calculator, all right, This is in radians, but degrees would be the same, okay? The problem is that it can't identify when it's a pi off of the solution. And so we have to make sure we either add pi, right, to the answer or not. And that depends on which quadrant it is in. So in order to identify, I need to similarly calculate for sine and cosine. Actually, let's do that. So if we were in quadrant 4, all right, because the initial graph of tangent's first period is actually negative pi over 2 to pi over 2. So if it's in quadrant 1 or 4, tangent is actually exactly what the calculator will calculate. But if it's in 2 or 3, you have to adjust it by pi. So tangent is a really, really fun one, all right? I was like, if you recall your trick, I was like, so that's why we're refreshing. Because like, this is one of those weird things that everyone forgets. All right, so if we are in quadrant 4, delta will be negative 0.3218. Or if we are in quadrant 2, delta will actually be negative 0.3218 plus pi, which is actually 2.82. And it's always like this. If you're in quadrant 2 or 3, so we just need to discover what quadrant we're actually in. Since we only have tangent, well, that's super easy. Let's identify for cosine. And for sine. Because I really need both of those to help. Now, be aware, I'm putting in the exact number here. But what do I actually care about? Do I care exactly what they are?
Just their signs.
I literally just need their signs. But I did the full calculation. Even though, as soon as you put it right here, I think I know what your signs are, right? That's all you actually. Okay, so if so we identified we're in quadrant 2 or 4.
2.
All right, and yes, all right, cosine, all right, is negative, which means, oh, I'm over here, sine is positive, oh, look, it also lined up. So that's super helpful as well, because even though I might only have needed one, it's nice to verify, because if all of a sudden you ended up, this said 2 or 4, and you got that I'm in 3, then I feel wrong, right? So I want to make sure that everything lines up. So we are clearly in quadrant 2, all right, because of that, which means that I do need to add pi for the proper shift. And that's the only tricky part, which is why I wanted to do this. So finally, that means u of t can actually be written as 0.527 cosine of 6t minus 2.82. Also, remember the general form. This is another note. The general form is subtracted. So if you get a positive delta, don't flip that sign, because the general form actually does have subtraction here. So, and remember to switch it to positive if you end up with a negative delta. All right, and then just as a note, and then I could put that in my calculator. But the other nice thing about this and actually it's pretty nice. The nice thing about this, and obviously what is about that value up there?
Amplitude, it's about 0.572.
It's about 0.527.
Or sorry, I had it backwards.
Yeah, it's it. I'm just gonna write 0.5 because I was like, it's pretty much. I was like, that's the best part. Okay, and remember that this is used to identify periods. So 2 pi divided by this number will give us what our period is. But yes, that's why we like this form, because you can sketch this out, and I could identify this in more detail. But usually at that point, you put this one to your calculator, and the values line up with the information you have. Okay, so now, we can adjust and let's add damping. So with damping, that adds our middle term back in. All right, which means that when we would solve this, we end up with the double root solution. All right. When we solve that and it's equal to 0, we end up with double root solution. This indicates what we're going to be identifying is our critical damping coefficient, all right, which we indicate as gamma CR. You can always calculate this one, okay? Because what we're going to be doing is identifying if it is critical damping, under damping, or over damping quite a bit. So with this, all right, again, once again, it's a relationship of M and K. We can solve for that coefficient, and it is always going to be this equation. In this case, in the critical damping situation, when I solve the characteristic, all right, and I solve for gamma, it actually ends up being equal to the critical damping. Yes?
Is dampening like a form of friction, or is that gonna be like?
Is this external or just like the inherent properties of the spring losing its stuff over time?
It depends, like, it depends if we have a damping force usually added. That's how we're gonna say it. But I mean, a damping force, right? When you go over a speed bump, right? And your car stops bouncing, what's the damping force there?
Just the
The
loss
shock
of heat and
resistance,
energy
right?
and everything from the shocks and stuff.
The shocks, yeah. So it's not just because when they first built cars, right? They just had springs, and afterwards, right? They go over a speed limit, and they were like, "Oh wow, okay." So it was like, and so ideally in most cars now, do we want under damping or over damping?
Under damping, right?
Other way.
Really?
You want over damping. You want the shaking to stop immediately. So
Okay.
we actually tend most systems, you want over damping because you want it to stop immediately. Because yeah, you don't want to drive over a speed bump and bounce for 10 minutes, right? You want to drive over the speed bump and then immediately stop bouncing. So actually they do over damping now. Under damping, right? It means
The
that,
boat, like.
yes, exactly. We can't, and you can't damp everything, right? I was like, so whenever you can, we try and over damp.
Okay.
That's the idea. No, for us, we're usually just going to say we have an external damping force that basically is stopping the spring, right? We're implementing a shock on that spring to stop it, and it's always acting in opposite of the spring. So critical damping means that it's perfect, it perfectly damped and it fades out, all right, appropriately. Under damping means that it fades out slower than it would, all right? And then over damping means that it fades out much, much quicker. You can do all this by when we calculate our value, all right, from when we solve for our gamma or damping coefficient. We can always calculate the critical damping coefficient. And if it is greater than, that's over. If it's under, that's under damping. So it's exactly the relationship. We describe it exactly as it's compared to the critical damping coefficient. And then, yes, so since, all right, we identified it as negative, it is always operating in the opposite direction, which means we don't actually have to worry about that negative. It is taken care of in our differential equation. So we can ignore the signs when actually solving for the force. All right, let's look at our example again. And we have similar information that we had before. So we still have our weight of 16 pounds. We have our offset distance as 8/9 of a feet. The only difference here, right? Additionally, we'll attach a damper. So notice didn't even specify what it was. Attaching a damper, all right, to exert a force of 12 pounds when the velocity is 2 feet per second. And once again, we still have no external force acting on the system. So the only change to all that initial information we had all right, so this time we actually need to, and then we still have, the mass was still the same, 0.5 slugs. K is still the same as well. 18. The only new step is now we need to find our gamma coefficient. So all this info exactly the same as we had before. And the damping equation. It is, all right, the force related to the velocity. So, okay, we have a velocity of 2 feet per second. And our force, which we can just put in as 12. And then we solve that, gamma equals 6, right? The units are irrelevant as well. This then creates, all right, our entire differential equation now. Same equation, but now we actually do have a middle term. So when we solve our characteristic equation, and multiplying that whole thing by 2 just to make it a little nicer. Because this becomes r plus 6 quantity squared equals 0. And that would be r equals -6 with a multiplicity of 2, right? Double root. Then we can solve for our critical damping to identify, all right, what we are looking at. So the critical damping coefficient, is 6, right? The damping coefficient for this problem is 6. Hence, so critical damping is occurring in this situation. Be aware, and you're going to see it in the home fund. What it looks like in the graph, critical damping, over damping, they can look a lot similar. Critical damping can look anything from it fades immediately to that. Over damping almost always looks like this case. This is always over damping. But this one, I want to make note that this can look like critical damping too. Under damping, all right, and I'm not even emphasizing that. Basically, it's fading, but super slowly. Just so you're aware, those are basically the three cases. And critical damping, I've seen it kind of look like this. I've seen it kind of look like this. This is the one that looks the least consistent. Overdamping should always go, all the resonance goes away immediately. This one, the resonance takes forever to fade. Critical damping can be kind of either of those cases. Okay, back to the problem. So mu of t in this case is C1 e to the negative 6t plus C2 t to e to the negative 6t. Solve the initial conditions. And this one, all right, so this looks again a little bit more like critical damping or over damping. Also make note, can we turn this into the nice cosine equation?
I don't think so.
No, because what are we missing? There's no sines and cosines here, right? So I definitely cannot turn that one into the nice undamped equation that we had above. Critical damping looks like overdamping, looks like underdamping. All right, it kind of blends between them. I've seen lots of examples of all. Without a doubt, overdamping and underdamping, you a lot of times can really recognize those. But you wouldn't be able to recognize it's not critical. So notice again, the vibration dies out before it even gets going. Okay. And oh, this is exactly what I said, right? From a physical standpoint, critical and overdamping, all right, are preferred to underdamping. Exactly what I was saying. Shock absorbers in your car, hit a bump, you don't want to spend the next few minutes bouncing up and down. Okay, so now our forced vibrations. Undamped, okay, so now I'm going to remove the damping and we're adding in a force. So before we noticed those two cases were the homogeneous examples. Now when we add in the external forcing function, all right, we are back to the non-homogeneous case, which means we need to identify a complementary solution and a particular solution. So exactly what we were doing in the beginning. Now, good news, the only ones we're going to investigate for this spring case is sine and cosine. So we don't have to worry about variation of parameters method, and it's only that single case of undetermined coefficients. The other good news is because since these are the most two common forcing functions by a distance, these have actually been solved out in their entirety. The complementary solution, right, always ends up looking like this, and that results in two super interesting cases. All right. Omega 0 is not equal to omega, right? So the omega is in the forcing function. Omega 0 was from the complementary equation. Which means, all right, that if you have a cosine forcing function, your equation will always result in this guy. If you have a sine function forcing function, it always results in this one. Notice these two equations are really, really close, all right? R cosine omega t minus delta, exactly the same. F0, which is coming from the forcing function, mass, omega 0 minus omega, which comes from the complementary and the forcing function, right? This one has cosine, this one has sine. Notice everything else in those equations is identical. And really, those are the only cases that we want to investigate. Mostly because the interesting case is this one. When omega 0 equals omega, when the forcing function frequency is the same as the natural frequency, right, of the motion of the object, the equation experiences resonance, right? An oscillation in which it grows in amplitude over time. And that's the fun thing, right? Resonance is a term from what field of study?
Wave theory?
Wave theory, and heavily applied to what?
Acoustics.
Yes, music, exactly, acoustics, right? 100%. So resonance, this is the really, really interesting case. Notice it has two cases based on the forcing function as well, and they look really similar to those other ones, right? Still have that same piece, forcing function, but now notice, all right, this looks a little different. But the idea is that we could solve this down and you could do undetermined coefficients to find it, but we are going to use the results here since these are the only two that we need to identify. And what we want to identify is the relationships between them, which is more interesting. So I have a 3 kilogram object, all right, so we're now in a metric, which is attached to a spring and will stretch the object 392 millimeters by itself.
Millimeters and centimeters, brutal.
Tricky, right? Sure.
And Newton to the meters.
There is, yes, you're ahead of me. There is no damping in the system, and a forcing function of the form is attached to the object. Systems will experience resonance. That's the big part. If the object is initially displaced 20 centimeters downward from its equilibrium position and given initial velocity 10 centimeters per second upward, find the displacement at any time t. So yes, you are absolutely correct. All right, so let's start with the easy one. Mass equals 3 kilograms. And you are absolutely correct because we want, all right, newtons, we want to be in newtons, we want our force in meters. So yes, I want to convert everything to meters. Also, what other thing that we're going to use really fast uses meters? That is in our equation.
Like how it's speed, it's velocity, or the actual dampening coefficient.
All right. In order to solve for K, I set mg equal to KL. G uses
Meters per second squared.
Is that what you just said?
No.
Oh, okay.
No.
And so, yes, that's the other way, but you're absolutely correct. All right. However you got there. Got this one. F0, right, which is that 10 from the forcing function, just an FYI. Also, I'm going to use 9.8 meters per second squared. And I can set up my initial conditions as well. Once again, these always start with initially. Initially means time what? 0. All right. Displace 20 centimeters downward, which means
Positive 0.2.
Oh, positive 0.2. Thank you. And then 10 centimeters upward, which means positive 0.1. Yeah.
Yes.
Negative. Oh, negative. My mistake.
Oh, because it's going upward.
Yeah. I was like, tricky. So I was like, that's the biggest thing to just pay attention to, right? Everything is reversed. Okay. I was like, those, in order to use those equations, you need to set up your conventions appropriately. I was like, so that's the big part. That's why we use it downwards. Otherwise, it's got to flip all the signs.
Yep.
Okay. All right. So K equals. Now I skipped this a lot, but I like to try it again. Mg equals K. which just means KUs. Now, here's the big one, and this is what I was talking about with identifying omega. Omega equals square root K all over M. This system, we were told, right, has resonance. So, omega equals omega 0, which are 5. So we actually, even though we didn't initially have the information, all right, for our forcing function, because notice in the equation, f of t equals 10 cosine omega t. I can't proceed to solve this until I know this number, okay? There is nowhere else, if this did not say it experienced resonance, if it said it did not have resonance, I can't solve this, all right? Not without having omega, a variable, in my solution. All right, so then we can actually create our equations. Now I have an equation with some initial conditions. Once again, always still start. I'm always going to start with the characteristic equation, solving the associated homogeneous equation. So, all right, we had a sine forcing function, cosine, we had a cosine forcing function, which is, again, I'm just pulling this equation down with the cosine forcing function. So I'm pulling this one down because I need to initially find C1 and C2. But I should have just about everything to plug into my equation. So simplifying it down, all right, we still have the work of applying the initial conditions, take a derivative, all right, solve that down. Details of this, but this gives us now the big thing is that a sum of sinusoidals kind of feels like a moot point, but the big part here is I can still reduce two sinusoidal functions into one. And that's really, there's not a ton of work to do here. We're only looking at a couple of situations, which means that we have determined functions, which means this is the interesting part, is turning that into something we understand, and then a forcing function, which is basically attached to it. Which means solving for R and delta. So when I solve that delta, once again, that's negative, which means tangent's in 2 or 4. Again, you have the same issue if tangent is positive because it's in 1 or 3, so you still need to do the same check to identify if you are in 1 or 3. Okay, so cosine is positive, sine is negative. All right, what quadrant are we in? We're in quadrant 4. Which means, okay, do I need to add pi to, no. So delta is just
Negative 0.1.
negative 0.1. So again, knowing when you don't is important as well. And since that is negative, remember the form, that becomes positive.
I was gonna say, is this gonna grow and grow and grow and grow?
That's what resonance is, and that's why these are really beautiful looking graphs. So, yes, by definition, resonance over time increases in amplitude, actually becomes, this forcing function becomes more important than actually the other piece. But that's the initial idea to find it. But with resonance, right, it grows over time. So they're actually really great functions.
That's cool.
The force damped vibrations, this is the all bets are off case. So, because now we have every single force being applied here. I have the external force, I have the damping force, right? We have our gravitational force and our spring. So with this, all right, the whole idea is that these you need to solve all the way out because there is no nice situation like we had here. We had our equations because we're only going to look at a couple of particular cases. We're still only going to look at sines and cosines with forcing functions, but the problem is this you need to solve as a complementary solution and undetermined coefficients or variation of parameters, right? In order to actually solve this down. There is no shortcut here. Also, absolutely cannot as we cannot simplify it to this form, okay, like we did in the other case. Whenever possible, do it, but if you have all four forces acting, do not attempt to write it in this form, because it actually it won't work.
This is getting to like the three body problem kind of stuff.
Yes, this is everything happening. I mean, there's four forces. We have four forces, all right, and so this is the most complicated case. So this, we grind out all the way. But we're going to start with our same setup. All right. We still have the same forcing function, all right, with resonance, but now, all right, we're adding a damper back in, which will exert a 45 Newton force, all right, when the velocity is 50 centimeters per second. All right, so still have a lot of the same info that we had. Still have resonance, so omega 0 equals omega. Now we're adding in our dampener. All right, we have our Newton force, which again, one more emphasis, as you mentioned. All right, why we want everything in meters. So 50 centimeters per second means
25.
25. So our IVP now. So we have all four forces, our characteristic equation. Solve that down does not come out to nice numbers. But it does come out to distinct solutions. So our complementary solution. So this is back to identifying, again, the full way out. So if I have my solution, okay, so I solved my homogeneous piece, right? In order to identify my particular solution, if I have 10 cosine 5t, what do we need to do?
Turn in the sine cosine.
We have to use undetermined coefficients method, all right, and guess and have an appropriate guess, right? Because what we call g of t, let's call that f of t, right? But g of t was 10 cosine of 5t, which means our particular guess and absolutely, and do you remember how to write it?
Is it
I know
A,
this was before before this last test.
it's like A cosine lambda t or something like that, and then plus bravo,
And in this case, how about 5?
yeah. And then plus beta or bravo cosine. Oh, okay. Okay, I had it backwards. I said sine first, but
Same difference. Yes. All right. So we have our particular. Then do we remember what we need to do?
insured coefficients are like particular.
Yeah. This
Wow.
we have to solve them though. Remember how we were saying, oh, stop, like we're going to stop solving these. This is application, right? Which means we have to solve this all the way down. I take the derivative. And I'm going to take the second derivative. Technically, I call them as u's, but same difference. Okay. And I'm going to plug all that in.
Back into the characteristic equations.
All right, I wrote that all out just because I wanted to emphasize, remember how nice it is to not have to solve for these coefficients. Because be aware, this is not, I'm not solving for the initial conditions. I'm solving for just the coefficient of the particular solution, right? So remember the stages here. This is why this is the toughest, okay, longest, all right, method, okay? And you could do this method on all of them. We have those nice shortcut formulas to try and simplify our lives. But when we have this case, we need to do all the steps. All right, but at least to that stage, the particular solution actually becomes, once I solve for the coefficient, I end up with 1/45 the rest of the details, sine 5t. We saw several methods. We did this by hand several times. I was just re-emphasizing because it. All right, which gives us the general solution. Then we still need to solve for the initial conditions. So notice that the details become a lot. All right, so the actual solution becomes oh, darn it, it's a negative. This one's actually okay, right too.
So we'll kind of get into like a steady state where it's not,
You stole,
Sorry.
stole my finale.
sorry about that. Just the way you drew it, I was like, that's kind of cool.
Exactly. So, yes, it is exactly, this is exactly defined as steady state.
In theory, I'll do that forever.
Yes, then it looks like this part forever. The forcing function 100% takes over, all right? We have, because it becomes the forcing function becomes the steady state solution.
So basically, the two parts kind of drop away. The only relevant parts that 1/45 sine 5t.
Yep.
Okay.
I was like, as the numbers increase, this basically takes over the entirety of the function, all right? Because by definition, what do E functions?
They either blow up or blow down.
Okay, negative E functions, you're absolutely correct.
Go to 0.
They go to 0, so these basically disappear. And so this becomes the steady state function.
Cool.
Yeah, no, I was like, so the point is on the home fund, definitely, I mean, graph them, like, look at them, like, they actually are, you see lots of, it was like fun graphs, I was like, I like to see, I was like, those graphs, they're really nice. All right, that is everything for chapter 4.